Okay, apparently everybody's here where they're supposed to be, so let's get started. Before that, as mentioned, these are some of the goals and non-goals that we have. I want to make sure it's clear for everybody. So one of the key things, well, two important things are what the goals are. We're going to cover, look into what SQL DW is and what it's not, and also the things that we won't do are obviously we're not going to read every single bullet in the slides. Some of these will be available for reference to all of you. And this is not the place. If you're looking for flashy demos and you're looking for somebody wearing a HoloLens thing, moving data around, you know, that's not going to happen. We're going to talk about the internals here. We're going to talk about how some of these things will affect a query that you send thinking, this should just work, right? And why it didn't, or why it worked really well. I do want to acknowledge our SQL CAT Customer Advisory Team folks, John Huang and Merched, who contributed hugely to this deck and the presentation. So it's one of those things that we maintain with SQL CAT. If you don't know what it is, talk to me offline. They're an awesome bunch of people that really work on the extreme ends of any of the SQL data platform services, including data warehouse, SQL Server, and so forth. So this is a session we're going to talk about SQL data warehouses, lessons learned and practical implementation tips. I chose not to call it best practices because over the year or so that we've gone GA and worked with a bunch of customers, we found that a lot of these are fundamentals, and folks think of best practices as the super advanced, you know, you got to be an expert, propeller head kind of thing to do. Most of these things are really fundamentals, so that's why I'm calling it practical implementation tips. So I'm a program manager. I work in the data warehouse engineering team, and apart from working on features, a good chunk of my time is spent helping customers deploy some of the biggest or most complex solutions on SQL Data Warehouse. So I do spend time traveling to customer sites or working remotely with them and figure out how to get them to make sure they have the right architecture designs, and if they run into issues, figure out how to solve it for them. So before we get started, how many of you are current users of SQL DW? Okay, roughly half, so I'm guessing the others kind of heard of this thing, DW, we don't know what it is, let's go find out. Plus, it's really far to go to the other two buildings, I'm already here, why not sit in here? Then let's see what you guys do. How many of you consider yourselves a DBA type, or play a DBA at work? Developer types? Okay. Anybody into administration, whether it's storage or systems admin? Any security admins here? No security admins? Okay. Oh, we can say anything we want then. Any business people in here? Non-technical folks? I sometimes get a few of those. Okay. All right, so that just helps me understand and level set and how far we want to go. As mentioned in the earlier slide, we're not going to go into every single thing, but feel free to ask questions. I could probably go as deep as you want to go in the areas of the engine. I'm not a tools guy, so if you want to build pretty reports and stuff, that's not my domain of expertise, but I'll try and help you where I can. But just to make sure we're on the same page, actually one last question. How many of you have experience working with MPP platforms versus SMP? Okay, about a quarter of you. Really good. Actually, that's a much better ratio than I expected. So let's walk through what is SQL Data Warehouse really quick. And the goal is to make sure we're all on the same page here. So this is the logical architecture for SQL Data Warehouse. As you can see, this is a classic MPP architecture. There is a control node, or a head node, as some folks like to call it. And that's where all queries and activity connects to and gets submitted to the data warehouse. There are n number of compute nodes underneath. So this is where your CPU and your memory and all go to work on the queries that you submit. Beneath that, the bar at the bottom are all the different storage formats that you have, your MDF and LDFs. Those of you who are experienced in SQL Server, this will be very familiar to you. We store that in remote storage. It is not directly attached to the compute nodes. So every time we need to fire up a new data warehouse instance, essentially we need to make sure we have the control. We need to have minimum one compute node, and these will attach to remote store. It's just regular blob store in Azure Premium Storage. So think of that as, in this case, is DW 500. DW is how we measure performance. We call it service level objective. Essentially, it goes in increments of 100. It skips a few steps because of how the underlying distribution works. But just think of that as every DW increment that you go, you get more compute capacity, or essentially you add more nodes. So at 500, you can think of that as 5 compute nodes available to you, operating against SQL DW, where the files, where the data is stored remotely in premium storage. Now, if I were to bump this up to, say, DW 1000, I need to get more compute power, I need more horsepower into my DW for whatever reason. Auditors are coming, I need to go get these reports run really quickly so I can get these auditors out of the office as quickly as possible. Or maybe you really like your auditors and you want to slow it down and keep the auditors here for the next 2 years. That's your call. I like to get them out quickly, so what happens is, it's a simple alter database command, or you can go to the portal to do the same, and what happens is you will then bump it up into 10 compute nodes here, as you can see with DW 1000, and the same 10 compute nodes will talk to the same remote storage, but each one of these nodes will now handle fewer databases. So one thing I didn't mention earlier, you notice I've got all these little notes here that says DB, distribution DB 1, 2, 3, and 4. So the current setting, and don't start writing these things down and think, this will be the rule to follow forward. The current number of distributions, what we call distribution databases underneath, is 60. So every DW has 60 physical SQL DBs underneath that. This is the current number. It could be something we will change in the future. It's just an optimal number today based on the scale that we want to reach and balance that against what's manageable for the instance. So today it's 60, so you notice when there were 5 compute nodes, each one of those compute nodes managed 12 instances of distribution databases. You bump it up to 10 of these nodes, then each of them manage only 6 distribution databases. So you can imagine now each node has fewer databases to manage, and hence each database or each query that needs to hit the database will have a lot more resources available to it. The way this works is when you issue the command, we basically do the equivalent of a shutdown and detach. Think of it logically, not physically. We do a shutdown and detach, and then go attach the new 10 nodes to your remote storage, bring it back up, run recovery, and you're back online again. So this is how we enable what we've been calling true elastic scale, where you can increase or decrease the amount of compute you have in your DW without having to move data around. This is physically impossible to do in existing on-prem MPP solutions, where every time you need to increase the size of your cluster, you want to bring in more racks and so forth, you end up having to do redistribution of your data. This allows us to not worry about that, and that part of it is because we have remote storage. The other part is because we have a certain number of distribution databases, so we basically just connect to it. Again, logically, think of that as how you would attach a database if you were coming from the SQL Server world. So, why are we going through this primer? And some of you are thinking, this is basic stuff. I know this already. Well, those of you who are not very familiar, this is really, really important. More than half, perhaps 3/4 of the issues that I work with customers on, that people that hit problems, it's because they're not familiar with MPP. They think, I know SQL Server. This is great. SQL Data Warehouse. They both have SQL. It's got to work the same. I will take my existing data warehouse running on SMP SQL Server. I will plunk that as is into SQL DW. And hey, it doesn't work so great. I can't even get data loaded in there fast enough. What's going on? So this is why it's important. This is SQL DW is MPP architecture. It's the same underlying engine, same underlying code base, but there is an extra layer on top of that that handles the MPP layer. So when you submit a query to SQL Data Warehouse, it will first figure out how to build a distributed query plan, which then gets pushed down into each individual compute node, and there it builds the individual query execution plan, which those of you who are familiar with SQL Server are most comfortable with. So there is an extra layer there you need to understand. There's extra work there that happens, and that implies your design patterns will change somewhat, and your query optimization techniques will also change somewhat. Size does matter, but not only just in aggregate, but individual table sizes, particularly row count. This is not something where you want to drop every single workload you have out there. Those of you who use SQL DW, about half of you raised your hands earlier. How many of you are using it with less than 1 terabyte of data? Less than 500 gigs? Oh, good, okay, nobody. So a terabyte is roughly the boundaries that we want to go to. This is not a hard rule. Again, don't go out there and take this, write us down, this Joe guy from Microsoft says. Less than 1 terabyte, don't come here. No, that's kind of a general guideline we provide, that if you don't have enough data, this is probably not the best solution for you. You can make it work, but it may not be the best solution for you just because this is a scaled-out architecture, and as I mentioned earlier, there's 60 distribution databases underneath every single SQL DW. So if you have a terabyte of data, automatically that gets, assuming you do even distribution, that gets split across 60 different databases already. Each database has multiple data files. And the numbers, again, will change also, but just assume that that's going to be spread over at least 60 databases with multiple files underneath. So what does your 1 terabyte now look like per database? It becomes really small. And it's not just at the overall aggregate database level or data warehouse level. It's what is your largest table size? If your largest table is 1 million rows, yeah, that's somewhat interesting on a SQL Server perspective. If your table is 10, 20, 100 million rows, okay, that becomes a little more meaningful. Why? Because again, we distribute everything across at least 60 distributions underneath. If you implement partitions, that get distributed even more. So this is really important. You end up breaking your data into really small chunks, and then you try and operate against that, and you try and build distributed query plans, and you pay the overhead of that MPP layer, and you're working against a really small set of data, and you'll be wondering, why doesn't this perform really well? That's probably because you don't really have enough data to exercise the muscle. The overhead of the MPP exceeds whatever you gain from having the distributed engines, each operating independently against one set of the data. So really important, keep that in mind. If you have small data mart type workloads, if you have things that run traditionally, if you're running on a fairly small box, this may not be the best solution for you. Again, it's not a hard rule. There are some situations where small data sets that use massive amount of compute work extremely well in this environment, but those are exceptions. OLTP type reporting workloads, generally bad candidate, things that people like to go there and hit refresh every 5 seconds, typically not great candidates, with some exceptions where you can build either caching layers or hub and spoke models to that. Last point, really important, how many of you are actually responsible for designing your data warehouse schema? About half of you. Great. So everybody knows if you have a bad design, everything's bad from there on, right? Yes? No? How many of you had to tune somebody's workload and then went back and looked at their tables and decided, you know what, I'm just going home? There you go. Okay, a few of you. If it's important in SQL Server, it's critical in this place. There are a bunch of things that will cause you so much grief. We've seen basic schema tuning. Don't even look at the exotic stuff, just basic schema tuning, picking the right distribution columns to hash against. We've seen over 10x improvement in performance just by doing something simple like that. So do not underestimate how much time and effort that you're going to need to spend figuring this out. It's not rocket science, but if you don't do it, you will pay the price down the line. So enough about that. So what are good workloads for SQL DW? It is designed for data warehouse type workloads, not your traditional OLTP. So all of the existing rules that you're familiar with DW applies. Things that like to go in there out of 1 billion rows, likes to find 1 or 6 rows out of that 1 billion row table, typically not a good candidate. Again, there are exceptions, but they're not good candidates if your typical workload goes in there and pulls 1 row out of your entire table of 10 billion rows. By the way, 10 billion is very common in data warehouse workload. Things that like to go do a lot of insert and updates and deletes, those are typically not your good data warehouse workloads, and we'll explain why in the column store when we talk about column store later. Incremental data loading should be done in batches and not intended for real-time data, things that get fed every second or every 10 seconds or every 2 minutes. You start pushing 5 rows into it. Those are not great candidates for data warehouse workloads, and we'll talk about that in the data loading section. If you have a system that requires 5 nines availability, you can use this, but you're going to have to do some special smarts in your application tier to provide that level of availability. The SLA we have for SQL Data Warehouse Service is 99.9, and it works very well for most environments. But if you're running a 4 or 5 nines environment, you're going to have to do a lot of special work to meet that 4 or 5 9 SLA. So this is not something that will serve you right off the bat, so be careful with that. Really ideal thing is really go after workloads that have complex queries that need to work against large data sets. So things that you can look at and you've bought the biggest box that you can find and it's still not good enough, scale out is a good answer for you. So how do we get started? For starters, data warehouse typically gets data fed in from multiple sources. If you're lucky, it comes from one place, but essentially you will typically have data coming from multiple sources, whether it's your ERP systems, your CRM, your sales, and so forth. We have a lot of customers feeding data from SAP, from Dynamics, you name it, all these different ERP systems and so forth, push them in there. Now, you don't want to put everything as is into it. This is part of what we talked about, importance of schema design earlier. You want to figure out what makes sense to bring into it. You want to filter out the objects that make sense. You want to figure out which data is meaningful to bring in there. So this is the whole ETL process, but before you even get to that, figure out what you want to bring in. Don't bring everything in there and then decide, I will just delete and drop these later, because those become expensive operations when you put it into column store and it scales out into an MPP environment. So you can probably do that a lot cheaper and easier in SMP, but in this case, when you scale it out this way, and because we default to column store, this can become a fairly expensive operation. So figure out what you need and bring only what you need there. Make sure you have some way to push data into SQL Data Warehouse. This is an Azure cloud service. This is not something that sits on-prem. This is not something that you can go, hey, we'll just connect every 5 minutes or every 10 minutes or every 2 minutes, push things in there. You want to ideally have a landing zone like Azure Blob Storage or Data Lake or someplace out there where you can push it out and you can ingest the data in massive batches, and we work extremely well in those environments. Be careful where you choose your landing zone, because your data warehouse could be in one of the 30+ regions that we have around the world for Azure. You could potentially have sources coming in from around the world. Pick a good landing zone so it's co-located where your data warehouse is. Optimize for that loading pattern, as opposed to having your data warehouse, let's say, in West US, and your blob store is sitting somewhere in Southeast Asia or Australia, because a lot of your offices are based out there. You're thinking, I'll optimize for these guys feeding the blob store, but no, you should optimize for where the blob store can feed data warehouse a lot faster, because all these smaller things that feed into blob store can move a lot quicker, and the chances of hitting connectivity issues is much lower. But if you have to push things across the wire from Sydney to Western Washington, that's a long ways to travel. Even the speed of light, you'll see a gap there. The latency will matter. You're probably talking into the tens, if not hundreds of milliseconds latency. That makes a difference when you're pushing terabytes of data. So pick the right place and make sure you pick the right scheme when you put the data files into blob store before loading. Find the right format, and we'll give a little more detail and guidance later, but you need to make sure you pick the right forms also, so that it will optimize the load into SQL Data Warehouse. So this is just prepping before you even load the data. Some recommendations, there is a migration tool out there. There are also third-party tools that can either help you convert your DDL if you don't already have it handy, pull data out and push it into blob store. Thing is, remember, there are some, because this is MPP, there are also some, and it's also SQL Azure PaaS. This is not your SQL Server standalone or IaaS instance. There are some gaps in T-SQL Service area, so not everything will work. So, and all of these are documented. Make sure you check them out before you run into it. If your application has heavy dependencies on something like CLR, that's not going to work. You may be able to rewrite some of that in T-SQL. They typically may not perform as well compared to CLR. That's the whole reason why you had CLR to begin with. So take that into consideration. Of course, we continue to close the gaps, but for now, there are quite a few gaps you need to be aware of. Stay away from the singleton operations. We talked about that earlier. These are really unhealthy for you. Data loading can be simple logging or fully logged, depending on which model you choose. We'll go into that in a little more detail. Make sure you pick the right one, otherwise you end up logging every single row that comes across. If you're loading 20 billion rows a time and you log every single row, imagine what kind of performance you're going to get out of that. And the last point is really important. You're working against cloud service. Expect failures. Even if you have a dedicated line, a leased line, or even express route, you could have some network congestion that comes in and causes timeouts. Something could happen that will take your connection out, even for just 2 seconds. If you don't have retry built into your workflow from the application side or from data loading perspective, then you end up having to babysit these things. So they're not hard to do. These things are fairly straightforward. Just do a retry. But if you don't have it built in, then you're going to have to deal with failures manually. So a couple more things on data migrations. Some of the compression formats that we support that we can read directly when you're loading data, these are the common ones that we use, so you don't necessarily have to convert everything into plain CSV. Some of these formats are supported as is when we load using Polybase. And when you're exporting, BCP locally is one of the fastest. If you're coming from other sources like SAP or whatnot, then you will have to go figure out what the optimal tools are for those environments to push through. Putting it up to Azure Blob Store, AZ copy is the de facto standard. A lot of people use it. It works extremely well. If you use SSIS, they will actually automate that process for you, but you need to have the latest Azure feature pack for SSIS to enable that. There are other methods of data movement, and I'll show you a chart later. For the most part, if it's not recommended here, you probably should not use them, even though they work, primarily for scale and perf reasons. So additional recommendations, Polybase and SSIS and ADF actually are the recommended tools to load data. So once you have things in Blob Store, Polybase is the most common way that we use to load data, and that's the fastest way you're going to be able to pull data into it. We've tested this with a customer workload in one of the proof of concepts, and we were pushing about roughly about 6 terabytes an hour using Polybase to load into DW. So that's pretty decent, 6 terabytes an hour. A lot of folks here don't even have their data warehouse in the terabytes range, so we can push fairly large loads into it. There are some important considerations. Loading very quickly into column store tables requires memory to go build the row groups and make sure we have good compression. So when you're loading, start at a minimum at medium resource class or higher. If you're running anything lower, you potentially end up with very poor quality segments, and I'll show you how to troubleshoot that later. But you want to start at the medium or large and move upwards. Now again, as things improve, as we improve the product and so forth, recommendations may change, but for the most parts, for loading, this will not be too different. Anything lower, so medium, you can also go down to small, or if you go into static resource classes, you can have more granularity, and those tend to get you into trouble rather than help. So for data loading, you really want to start at medium and move upwards if you think it's not moving fast enough. Polybase does support UTF-16 now. This is something slightly newer, but there are some gaps even with Polybase, so it doesn't do custom date formats very well. And if you have bad data, if you have certain rows that are bad in there, then it will reject that, but it doesn't give you a whole lot of detail on what was rejected and how to pull that. Now, some of you are nodding your heads already, so I'm guessing you faced those problems. We do have improvements underway right now to make that experience a lot better, so that if we encounter bad data, encounter bad rows, we will allow you to log that information and push that bad row into persistent store somewhere. So after completion of your 100 billion row loading, you can go back and look at which are the 6 or 20 or 100 rows that were bad and just go fix those. As opposed to today, if you hit a problem with that, you basically have to go restart, or you implement your own batching scheme to move chunks at a time to reduce your impact. So if you're dealing with that today, sorry for the bad experience, but we are making that better, and we do hope to get something out before the end of the calendar year. But don't hold me on the dates. So I mentioned I'm going to share some data with you on data loading. So as mentioned, Polybase and SSIS are really the recommended forms. ADF also. So the reason for SSIS and ADF being also recommended is they both use Polybase under the hood. So if you're already using ADF, great. That works just fine. Pull data from whatever sources that you're familiar with, push that into their warehouse, make sure you select the right workflow, and it will use Polybase to very quickly load things under the hood. SSIS with the Azure feature pack, I believe it was released in April or May, so I'm just going to state June here. So the original install of SSIS will actually use BCP protocol, which is really good for on-prem, not so good for Azure. So specifically Azure SQL Data Warehouse. So that's not a good place to be. It works, don't get me wrong. This stuff there's nothing technically broken about it. It works, but it works fairly slowly. And in a few slides down, you'll see why. So if you're loading data, especially loading lots of data, Polybase is the way to go. SSIS and ADF are great also. They both use Polybase under the hood. The cool thing about SSIS is, remember a few slides back, we talked about first extract your data, put it in some place in blob store, or have it locally and use AZ copy to move it into blob store, and then Polybase into your DW. So if you use SSIS, it automates that entire process for you. So you can use SSIS to extract from the source, and it has a workflow that allows you to copy the data into blob store and then load from blob store using Polybase, push that into DW. So in one SSIS package, it will do all of that for you. It even creates the sort procedures in SQL DW that basically mimics the Polybase scripts that we typically run. So if you are an SSIS user, good for you. Those of you who like to script in T-SQL, Polybase is the way to go. The last point, number 7 there, you have things like stream analytics, streaming data, Storm. That's not a good place to directly load into SQL DW. It works. Technically, it will work. You can push stuff in there. But as mentioned earlier, you're going to run into interesting problems later, performance issues later, when you start pushing these singleton rows in there, because the default table type that we use is clustered column store indexes, and you can certainly choose heaps and round robin distributions and so forth, but then if you're loading very large fact tables, those are really not the right schema options. So for fact tables, you really be looking at hash distribution and picking the right column for distribution. And if you choose that route, it will be clustered column store by default also. That's the right thing to do for fact tables. They are very large. And if you do that and you do singleton inserts, both the insert and subsequent query performance is going to be pretty bad, if not abysmal. So just keep that in mind. These are not good candidates. Some interesting notes about Polybase characteristics. It does provide you really, really good performance for non-compressed files, just because it's clever enough to go figure out, hey, if I point Polybase to this container, it's got 50 files in there, and each file is X size and whatnot. It knows how to go out there and figure out, hey, if this is a really large file, I will go grab chunks of it, and right now the chunk size is 512 megs, and I will grab each one of these chunks, and I will have parallel threads loading into it depending on what performance level their DW is at. So that means if you're running, let's say the example we had earlier, DW 1000, that means you have 10 nodes. I will go grab 10 chunks and load these guys in parallel and make sure that you can run really, really fast. And I know how to do the chunking automatically. You don't have to worry about that. Now, if you have compressed files, like gzip, for example, because we need to decompress the file before we can read and load that, decompression only runs single-threaded. So if you have that, we can't take one giant, 20 terabyte file, well, not 20 terabyte file, let's say 200 gig file in a gzip format. We can't run parallel threads against that. We only have one thread that can decompress it, and then we will grab one thread to go read. So if you're using compressed formats, you might want to chunk it out into multiple smaller chunks, so that way we have one thread running for each file. For uncompressed, we know how to automatically go chunk it out, and we will automatically run multiple parallel threads depending on what DW setting you're at. So just something to keep in mind. So if you're wondering why some of your Polybase loads are a lot faster than others, this might be the reason. The other guidance to take away here is if you have anything bigger than DW 100, 100 is one node. So if you have 200 or 1,000 or 6,000, or most recently we just announced this week, we can go up to DW 30,000. So try and think of it as the number of files you have should be either equal or greater than the number of slows you have divided by 100. Because that pretty much tells you how many nodes you have, and you want to hit that really hard in parallel. And why does that work? Why do I keep talking about the parallel thing? What's so special about Polybase in parallel? So remember, this is MPP architecture we talked about earlier. There's a control node notion, and all your connections and communications, your queries, all go through the control node. So in this case, a client that wants to go talk to SQL DW, and client could be queries or loading data, it would basically send that to the control node, and whether it's running the query or loading data, it doesn't matter. They all go to the control node, and the control node will figure out, you're trying to run a query. Great. I'll build a distributed query plan, I'll push it out to the compute nodes, and it will go out there and fetch data. Now, then some users get really smart. They're like, hey, I've done this before on premises. I'll just set up multiple parallel clients in the front end. That way I can have massive parallel loads. SSIS allows you to do that. It's been doing that for years. But you can't forget, in DW or any parallel MPP architecture, you can set up n number of clients here, and they're still all going to talk to the same control node. So you will very easily saturate that control node if you're loading terabytes and terabytes of data. Queries, I'm hoping you're not querying and pulling back terabytes of data. Those of you, how many of you are still dealing with select star and nowhere clause with your users? Anybody have to troubleshoot that lately? Okay, a handful of you. Nobody here writes those kinds of queries, right? Ever, right? Sure. So how does Polybase solve that? Well, we play a little trick. If your data is already in Azure Blob Store or ADLS, what happens is, however many nodes, as I mentioned earlier, however many nodes you have, we basically know how to do direct loading. We bypass the compute node. So when you issue a load using Polybase or SSIS and ADF that uses Polybase under the hood, we basically go hit the compute nodes directly, and they load to the files directly. The MDF and NDFs that's sitting in remote storage, in premium storage, we push that through directly. We bypass the compute node. So as many nodes as you put, this is essentially DW300. If you bump it to 1,000 or 6,000, that would be 60 nodes. We will load 60 nodes in parallel. That's how you can make really fast, and that's how we get about just over 6 terabytes an hour. So that's a boatload of data you can push through. And we're not even done there. We're going to push that significantly higher over the next 6 to 9 months. So if this is the way you want, if you have massive amounts of data to load, this is the way to go, and this is why. We doing okay so far? Questions? Sir? So sure. So the question is there a similar Polybase capability with Azure SQL Database? Unfortunately, right now, no. But you could still do the remote queries and whatnot, but this advanced loading capability, that's not available today. If that's something that's interesting to you, send in a wish request on user voice, and in all seriousness, we look at that every day, and we figure out which are the top requests from customers. And if some of these have high votes, and to be very clear, they have high votes and good comments and descriptions in there, because people are smart, right? It's like, hey, I really like this feature. There are 6,000 employees in my company. I'm going to send a mail to all companies and say, everybody, please go vote for this feature. So if there's high votes and there's no comments and all the names look about the same, that's kind of iffy. But if you go to user voice and you submit and provide valid reasons, and a lot of our customers do, that really affects our prioritization of features. So if there's something you care a lot about, go vote on user voice or submit your request on user voice. So data loading with Polybase and Create. So let's take a quick look at what creation and loading looks like that I just walked through. So this should be fairly straightforward, and we get this question pretty frequently. Can I create or delete data warehouses from Management Studio, SSMS, or using T-SQL? So yes, you can, except that you got to connect to master to be able to do that. So the syntax is fairly simple and straightforward. Those of you who are familiar with SQL Server syntax, all of that stuff looks very familiar, except this line right at the bottom here. You need to specify the options addition equals data warehouse, and service objective is basically the DW level that we talked about earlier. You can specify 200 or 1,000, whatever it is. It goes up to 6,000 today. In the very near future, it will go up to 30,000. Max size simply means that you can limit the size of your DW. So we support up to 240 terabytes on disk space. That's just a limit that we decided that's a fairly reasonable balance today. With clustered column store indexes, this will typically compress on the average of 5x compression, which gives you a little over 1.2 terabytes of data. We've seen compression go as low as 3x, and we've seen compression go as high as 20x. So there are customers loading up there, and their compression ratio is over 20x. So you can easily support multiple petabytes of data today. So it really depends on your data type and your schema and how things play out. So, but this really is the command to go run that. So we can come up here, and I'll put this in a different screen where I've got master. I'm connected to master. Whoops. Let's do this again. I'm going to let this run. It'll take a couple of minutes to go out there and create. So after you have it created, you can figure out what your current data weight DWU setting is, what your performance slow is. Oops. Decided to disconnect while I was asleep. Okay, that was just a dummy query to get it to reconnect. So let me try that again. Let's see. So that screen's okay. This one doesn't want to go run. I know what I did wrong. This did not switch. Let's make it faster. So you need to run this from master also. That didn't work earlier because I was in the user data warehouse. So if I run this from master, it'll have a list of all the databases or data warehouses. So if you're not already familiar with this, there's a notion of a logical server in Azure, and a logical server can host a SQL DB, it can host a SQL DW, it can also host a stretch database. So these are all the different data stores that we can host within a SQL server. The S for server is lowercase s. This is not the on-prem SQL Server product that you're familiar with. So as you can see here, we've got this retail transaction data warehouse. It's at DW 6000, that's the current max. And I've got the previous one that I created, DW 200, and the one that I just ran for this guy. It's in the midst of creation, but you already see the entry in master, which tells you it's going out there and creating that, and it's basically creating the 60 distribution databases. Once that gets done, then it will turn it loose, and we can go operate against that. So it's fairly straightforward. And the same thing, if needed to drop the database, you need to go to master to drop that. You cannot drop it from within the context of the same database. So that's something different from SQL Server. So let me go ahead and close this. And we created it at a specific DW level, but if you wanted to go change that, it's fairly straightforward. All you got to do is alter database, modify, and service level objective. Now, the one thing that we can't do is pause and resume. So I kind of went over that pretty quickly in the architecture diagram earlier. The really nifty thing that we can do when we separate compute from storage is we can pause compute. So what that means is, if I don't have any users hitting the data warehouse at this time, I can go ahead and hit pause and incur 0 compute charges. So you will still pay for storage because your data's all there, but I don't have to pay for compute if I don't need that. And we have a handful of customers that do this regularly. So what they do is they have a lot of data that they pull from multiple sources. They push it into the data warehouse. It runs at 6,000 DW, the maximum compute they have, because they run some really complex aggregations against that data that they pull in. So this happens usually in the 3rd week of the month. Push all that stuff in there, do these really massive computations. Once that's done, the result of that computation gets pushed to multiple SQL DB or analysis services tiers. So they push that out there and they shut down the data warehouse because they don't need to touch that anymore. And all of that aggregated data, all the outcome of that from these DB and whatnot, they take that and they sell it to other users. So they basically make money out of collecting a lot of clever data, augmenting that data, adding value to that data in the transformation, in the aggregation. They run in DW, they run at maximum compute capacity, and then once that's done, they put the results somewhere else and they start selling it. For the rest of the month, so the remainder 3 weeks of the month, they basically start selling that stuff to the customers, and come 3rd week of the next month, start all over again. Bring up the DW, run these things, pull the data out, and then shut this thing down. So this actually worked extremely well for in some environments. Sir? So let me see if I got the question right. Do you have plans to dynamically scale the compute nodes? And I'm guessing when you say dynamically scale is without terminating the connection the way it currently does. Because we do scale dynamically, except that your connections get knocked out and you basically have to reconnect, right? So that's on our roadmap. That's not the highest priority item right now. We do get a few customer requests for that. If that's important to you, talk to me after this about your use case, but certainly go to user voice and vote for that. So we have the occasional requests. We haven't got too many, which kind of surprised me a little bit. I thought people would care a lot more about that, but in all seriousness, we don't have that many people requesting for it. And again, this probably is because they're running traditional data warehouse workloads where they do have times where they can scale up and down. But we're starting to see a trend where data warehouse workloads are getting closer and closer to business critical type situations, and taking things down is no longer an option. So please do provide us more details and help us bump that priority if it really does matter for your organization. Sir?
So is it a valid model to have an on-prem data mart that we shut down that data warehouse after we pulled all of our reports back into our data center?
So the question is it a valid model or a valid design? Well, let me call it, is it a good design to have your data mart on-prem where you do all the work in the data warehouse in Azure as I described earlier, and then when you're done, you push the data onto the on-prem data mart? You could accept that you're pushing from Azure onto your data mart, so if it's a really small amount of data, sure, that will work great. What we see customers do almost exclusively, with very few exceptions, is they push it to a data mart that's sitting in Azure. That could be SQL DB, that could be a SQL server running in a VM, that's fine too. Or they push it into some other store, like Azure Data Lake, and have people run crazy ML algorithms against that. So all of these models are valid, whether they are on-prem or in the cloud, that's a different determination. We typically recommend putting it in the cloud just because, for starters, pushing it across the wire, you have to pay egress charges. So if you push a lot, not just consume bandwidth, but you end up having to pay for that. Whereas if it sits internally within the same region where your data warehouse is, then you just need to pay whatever the storage and compute that is.
So there's no egress charge?
If it doesn't cross regions, it will not have a concur charge. So, but once you pull it out onto on-prem, that technically is crossing the region, then you end up paying egress for that. It's fairly minimal, but if you're pushing terabytes every week, that will add up. So pause and resume that I described earlier, where we can just basically suspend and resume. We can't do that using T-SQL, but you can do that either using PowerShell, and I provided some sample scripts here, and these will be available as part of the presentation, so don't worry about taking pictures and trying to make sense of these words. But you need to run this via PowerShell, REST APIs, or go to the portal, and it's fairly straightforward in the portal, where all of the stuff that we did earlier, if you needed to create a new data warehouse, just click New and select Data Warehouse. If you wanted to scale, hit on the Scale button, and basically you'll get this nice sliding meter that you can go pull. Right now I'm maxed at 6,000. I can go bring it back down or up and go wherever I want it to go. So these are fairly simple to do, and if you don't like chasing the mouse around in the GUI in the portal, feel free to use scripts. The only thing that doesn't work using T-SQL is pause and resume. That one requires PowerShell or REST APIs, and that's because of how the authentication model works. T-SQL just doesn't play well there. So that's for the creation pieces, and for data loading, there are a few steps involved. You first need to make sure you have a database scope credential where effectively you are taking a secret, either a SAS key or the access key from your blob store, wherever that you've pushed the data into in Azure Blob Store, and create a credential. We will use that credential and present that to SQL Data Warehouse as an external data source. We will tell the SQL Data Warehouse where this data source is, so you basically have your standard URI that has your container name in Blob Store and the service endpoint. So it's typically go to your Blob Store and you will find all of the information in there. So once you've loaded stuff into Azure Blob Store, all this information will be available to you. We create a file format that basically defines what that stuff looks like. In particular, we define what the date formats look like and what delimiters we use. Highly recommend you stick to the standard ones. If you use some of the funky ones, it may not recognize that. I know there are a few gaps in Polybase that certain delimiters cause grief. The standard common ones that are comma separated, those all work just fine, and you don't need to explicitly specify those. Once you have that, and this is an important part, we talked about schema multiple times, this is where you tell SQL DW that this is the schema of the external data source I created. So it's called an external table, and what happens is you want to make sure you pick the right data types, the right length, the right sizes of it. Be very, very selective about the data types that you pick, because these things will have significant meaning when you load data, and also when you query data. It can affect the quality of your row groups that you build later. So things like that, don't think, I'll put everything as varchar 2000. How bad could that be? Well, it could be really, really bad when you try to compress these things. Hopefully nobody's using char all over the place. We do find some of these occasionally when people are migrating from mainframes and exporting data, and some of the legacy systems, they push things out, everything's in char 2000 or char 6000, and there's 250 columns with these kinds of values. It's just gonna fall over. So really evaluate your data types very carefully and pick the right ones. So beyond that, there's one data point here, reject value, as mentioned earlier. If you have bad data within your data set that you put in Azure Blob Store, you can specify, tell Polybase process that you will allow X number of failures before the job will fail or before the query will fail. So in this case, I picked 42 because it's a nice number, but you can specify any. Today, you can't get too much detail on what failed, only that it did. Moving forward, we are working on the improvements, as I mentioned, to provide a lot more information and persist the rows that failed in storage somewhere so you can go back and figure out which ones failed, and you can easily remedy that. So once that's done, one of the things I like to do is make sure that I check the role that I'm in, and don't worry about looking, there's a bit of an eye chart, I didn't bump that up earlier. Essentially, as I mentioned earlier, you want to be medium or large or extra large RC. There's a trade-off between that and the concurrency that you can use. The larger resource class you use, the fewer concurrent users you can handle, but if you pick a small resource class and thinking I will do more concurrency, you end up having bad quality row groups, and that's just going to cause you performance grief all down the line for as long as you have the data until you rebuild the index on the table. So pick medium or higher. And one caveat there to remember is if you are using the admin account, whether it's server admin or SA equivalent, it defaults to small RC and you can't change that. So those of you who are used to running as, I'm the server creator, so in Azure, you don't have the notion of SA, but you do have the admin account. When you first create a server, you provide that account. A lot of people use their own accounts as that. And then you will do everything off that account, and then you wonder, why is performance so slow? I already ran SP add role to extra large RC. Why am I not using it? Well, that's because, and this is the current design, and we're thinking of changing that. If you're the server admin, it doesn't matter what role you add it to, it will always get stuck on small resource class. And that would be really bad for loading. Queries are fine. Loading would be really bad. So always check that and make sure I'm the right slow. We've done that already, and the C task is a really simple process, and this is how you would typically load using Polybase. Create table, specify whether you want cluster column store or you just want to have everything in a heap or using clustered indexes. If you pick cluster column store, you got to provide distribution hash column, figure out which column. This is really important. Pick something that will give you somewhat even distribution, but don't look at just the data alone, at the schema alone. You need to look at your queries. I get this a lot, and I see this written up as best practices in a lot of places. Pick something that will give you really even distribution of your data. And when you run DBCC PDW show space use, if you look at all the different distributions you have, they all have roughly the same number of rows. And then they run their queries, and they find that the query is actually saturating 1 or 2 nodes across the cluster. Why? Because they distributed the data based on what the data looks like without considering the workload. So if your queries naturally end up selecting specific date ranges anyway, and you went and picked the date column as your distribution, your hash distribution column, so the dates that all resolve to the same buckets will sit in the same node, and if your query likes to touch just those dates, guess what? You have potentially 60 nodes, but you're going to hammer 2 or 3 nodes, and you're wondering, why is performance bad when I have the maximum performance level set? Well, that's because you thought about data distribution purely from a data perspective without looking at the queries, without looking at the workloads. So that's one of those things that I cringe when I see these best practices written up and say, yeah, go look at your data. It's like, no, that's not enough. You have to look at your queries. When you're loading, you can specify a different DOP level. This is actually one of the ways we mitigate if you don't have sufficient memory, if you're running at lower SKUs and you need to make sure you pack these columns tightly. That requires memory, and we automatically decide the maximum DOP that each node can handle. If you're finding that you want to run at smaller node counts and there's not sufficient memory, but you still want to load and have decent quality cluster column store indexes, then you can reduce the DOP so there are fewer threads running per node, and that will allow you to have more memory per thread, and you can have better quality segments when it's building these clustered column store indexes. So this is one of those little things that people don't pay attention to that can potentially cause you a lot of grief. Label. This is a nifty little feature in SQL DW. You can label your queries. How cool is that? If you wanted to troubleshoot, just search for the query with this label. Life is good. You don't have to hunt through a whole pile of potentially dozens, if not thousands of queries. Go find one that has this label that you care about and look at that, and you can figure out what it's doing and what resources it's consuming and so forth just by searching for the label. You don't have to cull through a whole boatload of queries across the entire pile that's been running, potentially hundreds, if not thousands. So this is one thing that I highly recommend you use because it makes troubleshooting and monitoring a lot easier. So a simple example to see tasks into a heap. I'm just going to go run this here real quick. Let's see, it's changed this into something different. And this should just run for a few moments. And effectively, I'm finding the quickest possible way to load data into it, just pushing everything into a heap. It's just about 200,000 rows. And we'll let that run for a little while. So let's get back to the slides. So we talked a lot about schema design earlier. I showed you some of the different CTAS options where you can specify whether you want a hash distribution table. In this CTAS script I ran earlier was round robin. So these are the 3 different table types that you can load into SQL DW. Hash essentially uses a hashing algorithm against the column that you specify, and then all the values that hash into the same bucket will be placed into the same distribution database. So pick something that's fairly unique that will give you some reasonable distribution across the board. Hashing against state, for instance. There are 50 states in the US. Other countries may have more or less. That's typically not a really good pattern because 50, you're not even going to use all 60 distribution databases that we have underneath. Pick something that will give you a reasonable spread of distribution for your data. And again, look at that vis-a-vis your query against your workload. Don't look at your options for which column to pick purely by looking at the data. So pick a good one where you get good distribution for the data and the query will run against the data fairly evenly across as many nodes as possible. That's the whole point of MPP. You want to divide and conquer. You want to use all of the resources available to you. The one thing to pay attention to today is there's only one column that you can hash against. We have had some customers ask us for multiple columns that we can pick hash values against. Not too many. Again, if that's something that you care about, let us know, send us feedback. Round robin tables, if you can't find anything, and usually there are some smaller dimension tables that are good candidates for round robin. This essentially says, well, I don't care what it is, however many rows you have, I will just evenly distribute across all of it. I don't look at any column to figure out where to put it. As the rows come in, I will round robin distribute across the 60 distributions. So that's a very simple method. A lot of people pick that, but this could potentially have a huge performance penalty when you're using it for fact tables. This is really not recommended. And when you run queries, imagine if you have 60 nodes and you need to do joins between different tables. If it's evenly spread across the board, chances are you're going to be moving a lot of data back and forth to be able to fulfill those joins. The last piece, replicated tables. This isn't currently in public preview, so you can go ahead and implement that. It's documented in books online. And what this is it allows you to basically specify this table, and usually it's for small tables, and the current guideline is something 2 gigabytes or lower. These small tables, you want it to exist in every compute node available. So by specifying replicated tables, what happens is it's going to take a round robin table, and the first time that you touch that table, it will basically build a cache and put a copy of that cache in every compute node. So that way, if you run a query that needs to join against this replicated table, it doesn't have to retrieve data from any other nodes. It's already there. It already has that cache. So all of that join does not require data movement. So if you're a current user of SQL DW and you run explain, which gives you the distributed query plan, and I'll show you an example later, and you see this thing called broadcast moves. Broadcast moves simply means it's sending the same data to everybody. If you see that in your explain plan, it's a good candidate to experiment and test as a viable use for replicated tables. But go to the documentation online and make sure you follow the guidance in there on the size and the nature of the tables. For the most part, your dimension tables that you need to go join against these massive fact tables, those are good candidates, but not all of them will benefit. So review the documentation and make sure that you understand the impact and also figure out what's a good candidate. So I'm not going to talk too much about selecting a distribution method. We already talked about that quite a bit. The dimension tables, so your fact tables is pretty clear. You're going to build very large fact tables, and you typically want to have hash distributed columns. Your small dimension tables, you do have options where you can put them into clustered index, so it's a regular row store that has a standard cluster index on top of that. You can use round robin or replicated tables. And the one thing I wanted to call out here is we do have some customers that have basically giant dimensions. So dimension tables run into hundreds of millions of rows. And it's not very common, but it does occur. In those cases, you might want to consider using a hash distribution. Most dimensions are fairly small, in the few tens of millions of rows, and those are great for round robin. But in some cases, we do have customers with giant dimensions, and they're truly dimensions, but they're running into the hundreds of millions, closing to the billion rows. Those you may want to consider a hash distribution. Certainly, those will probably not be great candidates for replicated tables just because they're really large and they would saturate the nodes. So something to keep in mind. Data movement. Remember, this is MPP architecture. Whenever you need to join data, and most queries will have to join, not all, but most of them, you can't join across nodes, so you need to move data. We talked earlier about broadcast moves where things are pushed to every node. Hopefully you don't have too many of those, but more likely you will see a lot of shuffle moves, which means I'll take a set of this data and I'll move it to the other node, and I'll take data from this node and I'll move it to the other. So it's basically shuffling data around so that they can do joins. So this is really important, and that's why picking the right distribution column is really important, so that if you have these things distributed into the same nodes, if you pick multiple tables, including very large dimension tables, and they have compatible distribution keys, that way when I need to join, both tables already have data in the same node. I don't have to move data in order to perform the join. That can save you a lot in performance. This is one of those things where you can pay attention to. Again, go to the explain plan and look at something that says shuffle movement. That usually is an indicator to start investigating and whether or not you've picked the wrong columns. So picking the right one helps you when you reduce data movement. That helps you overall perf and scale of your application. It's close to impossible to get zero data movement, but so the way you would try and figure this out is find your most expensive ones and go after those. If you try and chase it down to zero, don't bother. It's close to impossible. It's a data warehouse. You're not going to anticipate every query that people submit. If it's a fairly low cost movement, don't worry about it. Indexes. So nothing really interesting here. Those of you who are familiar with SQL Server indexes, you should know all of the different index types, so I'm not going to walk through each in detail, but I do want to call out something about non-clustered indexes. If you're used to tuning SQL Server, the SMP box, you're like, I will build NCIs here, there, and everywhere, right? Build as many indexes as I like for better query perf, isn't it? Anybody disagree? I disagree. Indexes are not free. You got to maintain them. Indexes, every time you do updates and deletes, you got to maintain these things. They're not free, even for SMP. And it gets a lot worse with MPP. So use them sparingly. If you have, and this is not a good workload, but sometimes it makes sense, you have workloads that need to go pull one or a few rows from your 1 trillion row table in your giant data warehouse, NCI can save you at orders of magnitude in performance. We've seen 20x improvement in performance in some of these cases. So NCI does make sense even in a SQL data warehouse with clustered column store indexes. But you have to go find the right candidates and apply that. Don't just apply that, for running slow, let's go build a bunch of indexes. No, that will cause you more pain than help you. So if you've identified that, hey, you know, my workload is pulling a very, very small number of rows, or maybe one row out of this massive table, and it's very selective, that may be a great candidate for NCI. Question, sir? Is there a use case for a non-cluster column store? No, not that I can think of. It doesn't do anything good for you in a DW workload. So statistics. We're also database people here. I'm guessing at least most people are, including our developer friends. You know SQL Server is a cost-based optimizer, and in this MPP architecture underlying that are SQL engines effectively, and the cost-based optimizer requires statistics. If it doesn't have statistics, it replaces the cost estimates with constants, and you end up with bad query plans. So statistics are critical. We don't currently have auto-update stats enabled for everybody, but it is in preview, and some of our customers that have tested that are getting the same behavior as they would expect with SQL Server. However, one really important caveat here. If you have very, very large tables, and we're talking things are into the billions of rows, if you have millions, few millions, tens of millions, that's not considered large in an MPP data warehouse world. If you have tables that are running to billions of rows, the auto stats management capability is probably not the right one for you, because we use a gradient scale on managing statistics and building and updating statistics. So the larger the table gets, the smaller the sample size gets for the statistic that we build. So whether it's create stats or update stats, if your tables are in the billions of rows or into the tens or hundreds of billions of rows, you potentially end up sampling 0.05, 0.08% of your overall table size. How useful is a 0.05% sample when you have 100 billion rows? Not particularly useful. You will find your query plans aren't working very well either. You're not getting very decent plans either. So if you have very large tables, this is one thing to remember, even after we ship auto stats, which those of you who use SQL Server probably are familiar with, and they love the capability, I don't have to worry about it. Great, turn that on for all of your dimension tables. Those will work just fine. Your smaller fact tables, those will work fine too. If you have large fact tables into the billions of rows, highly recommend you manage that manually. Figure out, start with a sample size of 20% and then move up or down. You got to test. Sorry, there's no magic here. You got to test to figure out whether you get better performance as you move up or down. Don't go 100% right off the bat, because don't forget, if you want to touch every single row every time you rebuild your stats, that can be pretty expensive. That can run for a while. So figure out 20% is a good starting point, and you can bump up and down by 5 or 10% increments to see if you get better performance. That typically implies that you're getting a better query plan, and test that until you find a comfortable spot. So usually we find users hovering between the 20 up until the 60% mark. Very rarely do we see users requiring 100% sample. So it does occur sometimes, but it's not very frequent. So 20 to 60% mark is fairly common. Sir? So the group order by, so to build the query plans, we need to go figure out basically the cardinality of the columns and how large a bucket for each unique value exists. So let's say you have a trillion row table and you have 1 million unique values in there, and basically we want statistics to tell us, okay, in each of these unique values, how many occurrences do I have? And those things become really, really important when you need to do either a join or a group by and where. But order by it is less important because we need to perform all of these things first, pull that results together, and then we order that. So that doesn't actually affect us when we need to go retrieve the data. Order by only kicks in after we have the data, and then we need to go sort that. Make sense? Sir, one question and we need to move on.
Well, that's okay. Just go ahead.
All right. Well, I did say one, so you get that. How many histograms do you have in there? We currently have 200 histogram steps, and there's no way to adjust that, but there's active investigation underway to modernize that, actually modernize the overall statistics management. So that will probably change in the near future. I don't have a date for you, but currently it's 200 steps. Partitioning. Whole bunch of things we can talk about partitioning, but I'll stick with a very simple thing. Go back to what we talked about earlier. You have minimum 60 distributions under the hood. If you have 60 million rows, you're already just 1 million row per distribution database. Now, if you're collecting a year's worth of data and all you have is 60 million rows and you partition by day, you're going to get a couple of thousand rows per partition. That's going to give you pretty terrible performance, and we've seen that all over the place. Again, folks who are really used to SMP, it's one SQL Server, one table, and I'm going to partition that, and life is good, and whatnot. And then you bring it over, right off the bat, it's already 60 distributions. If you partition by day, that's 60 multiplied by 360. So that's the number of shards you have. So on top of paying the MPP price, you're paying the partition price, and you're operating against a tiny chunk of data in each shard. That's really not a good way to get performance out of this. So simple guidance that we have for now, and this will probably stay true for quite a while. Think about every shard, every table, if you don't partition, you want to have at least a minimum 1 million rows if you can. Anything less than that, we don't really like. If it's about 500,000, okay, we will still have closed column stores, row groups in there. If it's down to tens of thousands, you're going to get awful performance out of that. So think along those lines. If you're not into the hundreds of millions or billions of rows, don't partition. I have a table out here I'll show you that I've run in very large table without partitions, and it works beautifully just because we broke it out into 60 different chunks already. So the really important takeaway here is be very careful with partitioning. Don't over-partition your data. The partition scheme that you have in your SMP world probably will not work well in MPP. So rethink that. If you're migrating something from your existing SQL Server or Oracle or DB, whatever it is, anything that's SMP, you bring it over to SQL DW, rethink your partition scheme. By the way, anybody use Oracle RAC here? I have those interesting discussions. That is not MPP, that's SMP, even though it's broken out because you're still operating against a single database instance. So if you have partition schemes in there that goes by day or month, don't go that route. If you bring it over to SQL DW or any MPP platform, rethink your partition strategy. Because sometimes people think, I have multiple nodes, right? It's scale out. Also, no, that's still SMP. It has multiple nodes operating against one instance of a database. So that is not MPP. Row store and column store. I mentioned several times that we use clustered column store by default. So very quick refresher, just to make sure we're all on the same page. This is your traditional row store, column store indexes, and we have a deep dive session on Friday. So Shivani is the PM who owns it. I will be co-presenting with her this Friday. If you want to go really deep on clustered column store, we're going to cover that this Friday. But just very quickly, traditional data you store in row format, and we support that in SQL DW. We also default to clustered column store, which means we take a certain number of row groups. Right now, the number is about 1 million rows, and we build into row group, and the way we physically store them on disk is by columns. So if you have column A, B, C, whatever it is in your table, traditionally, you put the entire A, B, C, D, E columns, and you fit however many rows you can in one page, and that physical structure goes to disk. In clustered column store, we take the same tables, we grab 1 million rows, and we go figure out, okay, column A, column B, column C. Okay, how much of column A can I fit into a page? That physically goes on disk as is. So if I do a page read with a clustered column store, and I say select column A and C, I will only retrieve data that contains data from columns A and C. I don't bring the whole row back and filter only the things you care about. So the read becomes extremely efficient, and we do batch mode operations against that. We also have very good compression against that. And this is how we get really, really good performance out of this. This is how we get up to 20x compression out of it, because the chances of having repeated values within the same column usually is fairly high. So keep that in mind, because there are subtleties underneath, and this is not the place to cover that here, but there are subtleties on how these row groups are pulled together and how the segments are built and how we lay it in the disk, how we maintain compressed, basically closed groups versus open ones, and there is performance impact if you keep things open and very large. There is performance impact if you build these cluster column store indexes with insufficient memory. So there's a whole bunch of things there we will talk about in Friday's session. That's not intended for this group. But really, if you haven't looked at this before, you do need to pay attention to this. And when we partition, as I mentioned earlier, be very selective about your partitioning. So your traditional row group, your row store partition will kind of look like this, and you can have n number of partitions. These are basically your horizontal partitions. You're now spreading this for your column stores, and if you break that out into 60 distributions, you can very quickly see now you've got many little shards, each holding a tiny bit of data. You used to think my partition holds a ton of stuff. No. You broke into 60, multiply that by however many columns you have. Each page potentially has very, very low density, and the read operations no longer become efficient. So keep that in mind. This is why when we talked about earlier about the efficiencies and making the right decisions, it goes all the way down to what gets laid on disk. So these are things that happens because there's downstream impact when we physically lay the bits down on disk. Example of how to go partition, and we have some of these examples in the slides also. The one thing to note is that to implement partitions in DW when you need to, it's actually really easy. You don't have to create a partition function, you don't have to create a partition scheme. You basically tell us, is it range left or range right? And you give us the range distributions, and it will go ahead and create the partitions for you. So it's actually fairly easy to do. Just use it very, very sparingly. So querying. I'm going to wrap up the slides pretty quickly. If we have time, we'll walk through the remainder of the demos. So we talked about movement operations earlier. We shuffle move, partition move, and broadcast move. So we've described shuffle and broadcast. The other move, data movement operation is partition move operation. This simply means that after all, however many nodes that I have that operated against your data, now that I've retrieved everything that you needed, it needs to go back to the control node, so that control node will return the data set back to the calling client. So if you see partition move operation, don't worry about that. That's necessary for you to send data back to the client. But the other two moves, you do want to optimize and reduce. You'll never eliminate completely, but reduce them wherever possible. So query performance impacts, we talked about a lot of these different areas, so I'm not going to recover that. The one thing I will point out that you can very quickly check for skew using dbcc pdw show space use. It will tell, and if you specify the table name, it will basically tell you for each distribution. So you have 60 distributions. It will tell you for each one how many rows exist, and it will tell you the size of each. So that's a very quick way to see how well distributed your data is. Some performance numbers that our SQL Cat has tested. I mentioned this is about 7 terabytes an hour at DW 6000, and it scales linearly. We scale from 1,000 to 3,000 to 6,000. The numbers scale linearly. So if you're loading into SQL DW and you're getting, 7 gigs an hour, something's not quite right there. When we scan, and this is only at DW 2000, we're hitting about 40 terabytes an hour to scan. So these are some of the perf numbers that we've worked through on customer workloads that we pulled together. And shuffle move, we talk about optimizing shuffle move, but again, the reason why I say is reduce them, don't worry about limiting them. We can move about 400 gigs an hour to shuffle data between the nodes. So as you can see, these things are built to perform fairly well, and they're designed so that when you add higher DWUs, it gives you more nodes. This really will scale your perf, assuming you've got your schema designed right, assuming your SQL is optimized. So this really does allow you to increase compute on demand, and you get better perf on demand. And if you're not getting pretty close to these numbers, you probably should relook at your workload or your schema to figure out what you're missing there, because these are not things that we cook up in the labs. These are things that we use customer workloads to test against. So these are some of the numbers that we've gotten. So last two slides, important lessons learned. Some of this we've already talked about. Pay careful attention to architecture and remember that you're designing against the cloud. The few things I want to really re-emphasize is skew is about data and queries. It pains me, again, to see all these write-ups, these blogs and tweets that people say, data skew, look at your data. It's like, no. Look at your queries and your data. If you look at just the data alone, you will find that you wrote queries that will hit 2 nodes out of the 60 you provision, and you're wondering why you're getting horrible perf. Pay careful attention to that. Statistics. I also see a lot of blogs saying, here's a little script that will enumerate through all the columns in your table, across all tables in your database, and it will create stats at 100% for every single column that ever exists. Like, but why? If we don't need statistics on the columns, why are you doing that? For dimensions, that's okay, because instead of trying to figure out which columns you're going to need, dimensions are fairly small, and creating stats against all of these columns usually is okay, because the cost of doing that is fairly low, and you basically cover yourself, because dimensions tend to get selected across multiple columns by different workloads. So that one's kind of okay. Fact tables, where you have trillion row tables, and you potentially have 100-200 columns in these tables, and you want to create stats against every single one of them, and they never get put into a where clause or a group by or a join, then why are you paying the cost of building stats for those? So be very careful about that. Certain things you should follow, be careful what you read in the blogs, and they're saying, just go do everything, and here's a free script to go do that. Well, good for you, burn a lot of compute. Microsoft makes some money out of that, but it buys you nothing. So, hub and spoke architecture, I see this a lot also. They'll say, put an analysis services or a SQL DB in front of his SQL DW. That will solve all of your scale and your concurrency and your latency problems. Maybe. It doesn't solve it for everything. And that is not free either. And free, I'm not talking about the price you have to pay for the service. Yes, you have to pay for that, but don't forget, when you build a hub and spoke model, it works extremely well in some environments where you want to have high concurrency that hit the same set of data repeatedly and you want to support 10,000 users. Wonderful, go build these hub and spoke models. But if the data changes fairly frequently and you keep having to refresh these models, or you keep having data that comes through that needs to be rebuild whatever caching layer that you have, that kind of defeats the purpose. You might want to investigate something else. And so be careful with some of these recommendations that say, here's a cure-all to your perf and scale problems. They usually aren't. We talked about interactive clients and drilling, so a couple of other things I want to draw your attention to. The pause and resume, the pause feature and the scale, the dynamically scaling, moving your slow up and down feature. If possible, drain your transactions. Make sure you don't have any write operations against that before you perform pausing or changing of your performance level, simply because when it reaches the new perf level, when the database comes online, we need to run recovery. And if you have a lot of open transactions, you killed something that was operating against 20 million rows, we need to run recovery, and that could take a while. So even though the database comes back online, you won't be able to do anything interesting until recovery completes. And sometimes people think, something's broken with the DW. I can't access it even though it says it's online. Well, no, that's because we need to make sure we bring it to a consistent state before you start running queries against that. Applications, if you're using third-party applications, a lot of folks will just repoint the application to SQL DW, change the connection string, and they end up saying, hey, perf is really awful here. Why? Well, that's because the application's used to doing a select star without a where clause and tries to do client-side processing. Well, that's a good way to DOS yourself. So imagine you have 1 trillion rows in there. I have a table in there, 1 trillion rows, about 26 terabytes in size. If you did a select star without a where clause and pull all that stuff back to your client, what do you think happens? How many of you are good friends with the network admins? If you're not, you're going to get to know them really well. Or the security admins for that matter, because you could effectively DOS your network. Pulling 6 of you running select star against a 20 terabyte table. Don't try this. No, I was going to say, yeah, go try this and see what happens. No, don't try this, because then you're going to get pulled in and you're going to say, the guy at conference told me to go try this, and everybody's going to come after me. The other 2 things to be careful with, if you use AAD groups, we do support Active Directory authentication or integrated with Active Directory. If you have your local AD federated with Azure AD, we do support that authentication method. Really handy. And a lot of users decide, I'm not going to add individual users, I'm going to add security groups. Really good. Well, okay, do you control who gets membership to the security groups? We find some of our customers are scratching their heads. Why do all these random users now pop up in my data warehouse and they're running queries? We don't know. It's like, who owns the security group? I don't know, some random person somewhere. It's like, they're adding random users. Every new employee that joins, they are adding it to the security group, and they all now have access, especially the admin security groups. They start popping in there. Everybody's admin here in DW. Be careful with that. And the last piece is we have replicated tables. This is a brand new on preview feature. It's a good way to warm that up. Remember, replicated tables is a caching solution where if you enable that, upon first touch of that table, we grab the data, we build a cache, we put it on each node available. If you want to have optimal performance, you probably want to enable that cache building before your users hit that. So every time you complete a DML or you've changed performance slows, run a query, select top one is an easy one so that you will pre-build that cache before users hit that. Because depending on the size of it, it could take a while for the cache to completely populate, and your users might be wondering, hey, you told me there's this new feature that will make my perf better. It was really good yesterday. What happened today? And so, well, you just bumped the slow up or you just loaded new data and the cache was invalidated. So one of the things to pay attention to, we're still tuning perf on that. So today, You may find the perf is a little below what you would expect for replicated tables, but do run this small optimization step so they pre-populate the cache in advance. You will save some of that performance grief, and in the future, just remember to automate that within your workflow. Every time you complete loading the data, you make major changes against your dimension tables, just go run a select top one. Once we hit that, we will build a cache. So, apologize, we were a few minutes over time. I have resource links at the end of this deck. If you have questions, I will be outside or along the side so the next speaker can get set up. Thanks a lot for your time. I hope this has been useful to you.